all these pictures. And eventually somebody found it. It's very difficult to see in this image, but it's a little spot. That spot is the Earth right there. And and the astronomer Carl Sagan of the Cosmos fame wrote a book called The Pale Blue Dot about that little dot. And about the dot, he says, because of the reflection of sunlight, so that shaft of light, that's just glint off of some metal that went into the camera. Because of the reflection of sunlight, the Earth seems to be sitting in a beam of light as if there was some special significance to this small world. But it's just an accident of geometry and optics. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. All right, so that kind of view is a view that says man is nothing, and therefore anything that says man is something is actually wrong. And this idea has been given a name. It's been called the Copernican Principle, also called the Principle of Mediocrity. And it's named after Copernicus, but Copernicus would have had nothing to do with this idea. This is not really a Copernican idea. But it comes in two flavors. There is a classical Copernican principle, which basically says, look, the Earth is just one out of many planets around and there are many stars. There's just nothing particularly special about us. And yet there is even a more sort of deeper one called the metaphysical Copernican principle that now goes beyond a scientific statement. It actually becomes a metaphysical statement that says we're not here for a purpose. The cosmos isn't arranged with us in mind. Our metaphysical status is as insignificant as our astronomical location. So the metaphysical one leverages the classical one to essentially make now a religious statement. And so what we want to do today is just examine this Copernican principle in light of astronomy and in light of what we have now learned. But before we do, let's just take a quick look at what this Copernican claim is about. The Copernican claim goes something like this. Well, in the olden days, we had Aristotle, and Aristotle had a cosmology, a picture of the universe, in which the Earth was at the center. Aristotelian cosmology placed the Earth at the center, and around the Earth were orbiting the various celestial bodies, the moon, the sun, Mars, Venus, and the other planets, and outermost, and all of these are in these crystalline spheres in the mind of Aristotle. And the crystalline spheres are in rotation around the Earth. And on the outermost is the firmament, the stars. And all of these are moved by a prime mover. Now, when Christianity, came about, when Christian thought was kind of put next to this cosmology, the Catholic, what we now call the Roman Church, they basically adopted a whole lot of this, and they just baptized it by saying, oh, that prime mover, that's God. Okay? But in fact, quickly adopting that cosmology ended up being problematic. One of the things that was a problem with the Aristotelian cosmology that was known very quickly was that there are certain objects in the sky, the wandering stars, which the word wandering is also known as planet. The planet comes from that. The planets didn't quite move in a way that you could expect. Like if you look at Mars in the sky, let me see if I have a laser here. But if this is Mars, as time goes on, Mars actually goes into retrograde and goes the opposite way and comes back. If it's moving on a sphere around the Earth, how is it that's moving backwards some of the time? So that sphere is essentially jerking back and forth, and what's that all about? And so Ptolemy in 2nd century AD said, that's okay. Mars is a perfect heavenly body. It is moving in a perfect pattern, which is a circular pattern. We all know that has to be that way. That was their thinking. But it's moving in a circle that is itself moving in a circle. So he called that an epicycle. And the epicycle basically was this little red circle here. So Mars is moving on that circle, and he says, look, that will produce this effect you're looking at. And then he was able to adjust the period and frequency and size of that circle to match the observation. And that works so well that for 14 centuries, there was no rival to Ptolemaic astronomy. It was like it was done. Astronomy's done. Every planet, you calculate its epicycle and different and all of that, and there's nothing else in astronomy to know. And 14 centuries later, Copernicus comes along. Oh, by the way, I jokingly at this point in the talk say it was settled science, if you've heard that term before. So then in the 15th century, Copernicus comes along, and he resurrects Aristarchus, his cosmology, which had the sun at the center. So he writes a little commentary. He passes it handwritten to his friend saying, I'm going to go with a whole different set of assumptions. And these assumptions more elegantly describe the motion of the planets. And in that set of assumptions, the sun is at the center, not the Earth. The Earth is revolving around the sun, and the other planets are revolving slowly, the outer planets, around the sun. So that from our vantage point, basically the retrograde motion occurs. Later on, about I think 100 years later, Galileo. So that idea of Copernicus, his book was published like when he died, and I think Copernicus just said this is a good mathematical picture. Galileo decided actually make measurements using a telescope he'd made of Jupiter. And when he looked at Jupiter, he saw that there were little bright dots next to Jupiter. And as he watched from months after months, this is a picture from Galileo's logbook. So there's Jupiter, and those little dots are moons. And he said, wait a minute, these dots are moving around as you look over months. Those are the satellites of Jupiter. And if they're revolving around Jupiter, they're not revolving around us. And so it's not true that everything is revolving around Earth. Also, on the notion of heavenly objects being perfect, he said with his telescope, he could look at the moon in more detail, and he was seeing craters. And the craters showed imperfections. They looked pockmarked. There were shadows. He could see the shadows on the moon. That's also his drawings. And so he said, the heavenly bodies are not perfect either. So Galileo went a long way towards basically confirming the Copernican picture, that we're not at the center, the heavenly objects are not really that idealized anyway. And so this heliocentric, or the sun-centric view kind of took hold. So you can see what has happened. Now we went from Earth-centered to sun-centered. And then you come fast forward to the 20th century, and you get to this man, Harlow Shapley. And Harlow Shapley was at Harvard. That desk, it's a rotating desk. Oh, I better get out of the picture here. The rotating desk, he would put his books on different parts, and he would just rotate it so you wouldn't have to move. But anyway, he did this measurement with a very big telescope in Southern California, where he looked at the locations of miniature galaxies known as globular clusters around our Milky Way. And he looked at how dense are they and where are they most dense, because wherever they're most densely kind of revolving around, that must be where the center of the galaxy is. And he said, they are about 20,000 parsecs away, and a parsec is 3 light years, so it's about 60,000 light years. Now he made a mistake in his measurement, so he was off by a factor of about 3. But the essence of it was that not only are we not the center and the sun is the center, now the sun is not the center, but something else in the middle of the Milky Way is the center. And so he said of this, Shapley said, the solar system is off-center, and consequently, man is too. So that seems to confirm that too. We are really not the center of anything. But Shapley thought that the Milky Way galaxy was the universe. That was the universe. But his arch rival, Edwin Hubble, also from Missouri, also showed that that is not true, that actually the Milky Way is only one of many galaxies. So we have this picture that the Earth is not at the center of the solar system, the Sun is not at the center of the Milky Way is not the only galaxy, and so it looks pretty right. Yeah, we're really not at the center at all. But does our removal from the center really diminish the value of where we are? That's a question we'd like to look at. And we'll do that using a new field called basically exoplanet science, study of planets that are not around our sun, but around other stars, extrasolar planets or exoplanets. And in particular, we're going to focus on a notion called habitable planets. What would make a planet habitable? So that if you went there, you could actually survive it. So that's the question. This field is only about 25 years old. It was 95 when the first extrasolar planet was discovered. To have a habitable planet, the first thing you need to know, is that the planet should be terrestrial. Terra means dirt or earth, and it needs to have actually rocks and dirt. So that actually, for us, dirt seems kind of mundane, but on a galactic or a cosmic scale, dirt is extremely valuable because those heavy elements are the results of generations of stellar explosions and stellar furnaces cooking these things up. So when you see dirt, remember how valuable that is. We would like to have a terrestrial planet, but actually a lot of the planets are these things called gas giants. Jupiter, for example, is a gas giant. If you were to be dropped on a gas giant, helicoptered in or something, you would just keep going down until the pressure would be at about 1 million atmospheres, where hydrogen becomes a metal. It's definitely not habitable. So you need a rocky surface to just stop at. All right, so first thing we need is a terrestrial planet, and that's important. Next thing we need is that terrestrial planet would be in what is called the circumstellar meaning just around the star, circumstellar habitable zone. Now, what is that? Well, if you get too close to a star, the energy output of the star is so high that you will boil off all the water, and the planet will just be a molten mess. If you go too far, everything will freeze. So you can't be too far, you can't be too close, you can't be too hot, you can't be too cold. You have to be just right. Some people call it the Goldilocks zone. And so in this picture, the green zone is where the habitable zone is drawn. Now, somebody made this plot, which shows the width of the habitable zone as, this was a 1993 plot. This is actually very optimistic in reality. But in our solar system, this is the various kinds of stars, from the red the red stars that are very low energy, they're red color, to the very hot A stars, which are bluish and very energetic. Our star is in the middle, and here's our planets. There is Mercury, Venus, Earth, Mars, Jupiter, Saturn, and so on. And if you look here, neither Venus nor Mars are in the habitable zone, actually. So the idea of actually, expecting life on Venus, based on what was known, now this is like 93 era knowledge, was already kind of excluded. It was already excluded. Now it's even more excluded. And we'll go into that as we get into this a little more. Let's talk about the fact that these edges of the habitable zone are actually kind of tighter than actually implied in this picture. This is a talk by someone named Francois Forget. This was at a conference in Switzerland a few years ago. And he was showing this result where basically they did this modeling. And what they found is that if you take the Earth and you come in by just like a few percent, I think it was 1 to 5%, you run into a runaway greenhouse situation, where the additional energy output of the star, because you're now closer, causes a lot of evaporation. The evaporation causes a dramatic greenhouse effect, which increases the temperature, which then causes even more evaporation, and so on. It just runs away from itself, and so that all the moisture ends up in the atmosphere. Then the as it's in the atmosphere, the protection of the ultraviolet light from the sun goes away because you're up higher. There's not as much shielding of the ultraviolet, and a process called photolysis occurs where the ultraviolet essentially dissociates hydrogen dioxide, basically the water and oxygen, from each other. So the hydrogen, being so light, goes way up to the very top of the atmosphere, at which point the protons from the solar wind just whoosh them away, and the planet becomes completely desiccated. So this is a runaway scenario, just 5% closer to the sun, and it's all over within a certain amount of time. The other side is not that much better. You get runaway glaciation, in which case the lower energy output, the energy insolation that you get, the energy reception, causes the solar flux goes down, the temperature goes down, you get more snow and ice, which has a higher albedo. Snow is white, so it reflects a lot of that energy back, which cools the planet down, which causes more snow, and you get a snowball Earth. It just runaway glaciation, and the planet is frozen over. So the Earth is just sitting at a knife edge, in a sense, of excellent climate. Another thing that is interesting, I'm going to just jump over that. It looks in this picture like every kind of star does have some sort of a habitable zone. But it turns out some of those habitable zones are not worth it. For example, these stars, the M dwarfs, the habitable zone has gotten so close that you get into an effect called tidal locking. That is this, where as you get too close to the star, the gravitational attraction of the star turns the spherical planet into a jelly bean shape. And that now the planet that is spinning feels what is called a differential torque, or basically the gravitational pull slows the planet's rotation down until the planet's rotation rate completely becomes synchronized with its orbital rate. When that happens, the planet always presents the same side to the sun, and one side gets baked and the other side freezes over. By the way, this is called tidal locking. It's locked to the Earth. The Earth is locked to the sun, for example, in that case. But an example of that is the tidal locking of the moon. The moon, only we see one side of it. We never see the back side. The so-called dark side of the moon is the side that is on the other side because the moon is tidally locked to the Earth. So this effect happens, and it happens rapidly as you get closer to the star. So so basically that those cooler stars where the habitable zone is close are, by the time you're that close, you get tidally locked. Forget, that habitable zone isn't worth anything. At the terminator, at the right where the sunset and sunrise, you would see that there might be a little bit of liquid water, but other than that is nothing. All right, so we've talked about the planet, the kind of planet you need, where you need to be, and what kind of star you need to be. We'll talk a little bit more about the kind of star. We saw that these red dwarfs, they're the small, cool ones that are actually, David, would you mind focusing this a tiny bit? I think it's out of focus a tiny bit. So these guys are so cool that, or it might be that that's the best we can do, and don't worry about it. There's 2 rings there, by the way. But the sun is sometimes in the astronomy books is called an average star. And if you look at this list of this sort of drawing of various types of star, it sure kind of looks kind of average. It looks reasonably average. But there's a couple of problems with saying the sun is an average star. And first of all, this average star is only 7% of the stars are like our sun. If you go this direction, you get tidal locking. If you go this direction, you get stars that are so energetic and so sporadic in their energy output that it wreaks havoc on the planet. So in fact, the stable energetic stars are right in the middle. And so you want to be right near the middle. But of the stars in the sky, half of them are part of binary star systems, 2 stars going around each other. The problem with binary stars is that there the planet's orbit gets unstable with these stars kind of jostling around. And so in fact, half of these 7% are actually no good either. You're down to 3%. And so in that sense, the average star is actually pretty rare. Now, so we talked about the planet, the star. Now, The star is in the galaxy. Well, where in the galaxy would you want to be? It turns out you can't be anywhere you want in the galaxy. Suppose we were close to the middle of the galaxy, so the nice, downtown. It turns out downtown has a supermassive black hole in it, and it will rip you to shreds if you get near it. So the downtown is really bad. Okay, go way out into the farmlands, way out, away from. It turns out that the abundance of heavy elements is so small out there because the generations of stellar formation has not taken place, and so all you have out in the farthest reaches are just hydrogen and helium, and there's no, if you want a terrestrial planet, you can't make it there. So to make it there, you have to be, on the one hand, close enough to get higher, what they call metallicity. That's astronomers' word for having heavy elements, but not so close so that you don't get, ripped to shreds with what's in there. The other thing you don't want to do is actually you don't want to be near the spiral arms either, because both the spiral arms and the center of the galaxy have a lot of supernova events. A supernova is when a star explodes. When that star explodes, its energy output is about the equivalent to the entire galaxy for those few days. So here's an image from Hubble Space Telescope showing a galaxy similar to the Milky Way. And here's one lonely star. There's 100 million stars here. And here's one star. And you can see it's just visually, it's about the same brightness as on the entire rest of the galaxy. When that event occurs, it sterilizes any possible life for light years around it. So you don't want to be in a neighborhood where these things are popping off because, it's not good. So in a sense then, what you want to be is somewhere at the right radius around the galaxy, but not in the spiral arms. You have to be near something called the co-rotation circle, where your rate of orbiting the center of the galaxy matches the rate at which the spiral arms are coming, so that you can always stay away from those spiral arms. If they come in like a wave swooshing over you, for that amount of time that you're under their influence, you're in danger. So that's all. So now we said the planet has to be right, has to be the right place around the star has to be right, the star has to be in the right place in the galaxy. But how about any galaxy? Would every galaxy work? Turns out our Milky Way is about one of the 3% top heavy galaxies. And what it means is that our Milky Way was able to produce heavy elements earlier than most other galaxies. And so those are what were necessary for planet formation. So in that sense, also our galaxy is special. Now, the actual list of what you need to basically have a habitable planet is actually a lot more. For example, you not only need to have these conditions, you need to have a magnetosphere. A magnetosphere, and we'll see that in a short movie clip that's coming next. A magnetosphere protects the Earth by deflecting the solar wind. So we'll see that in a second. You need water. Obviously, you need water for life, but you don't want too much water. And here's a picture from Interstellar, the movie. They arrive at this planet, it's all water, and they go, oh, well, that's no good. And that's actually right. It is no good if the whole planet is full of water, because nutrition basically is possible when water comes near land, and there are shallow places where the water is in abundance, and there is warmth of the sun and the energy of the sun. If you are all down into deep oceans, the chance for any sort of thriving of life is very low. You need a large moon. The moon stabilizes the axial tilt of the Earth. So we spin, or the Earth spins, and that gives us our day or night. And then the Earth's spin axis is actually kind of canted at about 24-ish degrees. So as we go around the sun, sometimes we have something we call summer, and other times we have that other thing we call winter. If the axial tilt was large, one side would just have nothing but sun all the time at a really steep angle. It would be scorching, and one side would be just deathly winterish. The other thing is, if the axial tilt were to just kind of do this a lot, which Mars does and Venus does, then the climate would get really messed up. It would be a very violent climatic change. And so the axial tilt has to be stabilized, and our moon in its orbit, because our moon is so big, it actually has an effect on the axial tilt of the Earth where it stabilizes it for us. You need to have plate tectonics, which give us our earthquakes, but it also basically recycle CO2 and minerals into the upper crust of the Earth. They have a very positive effect. You have to have a right atmosphere. If we're going to have large beings like us, we need oxygen. But imagine a planet where it's all oxygen. A spark, and the whole planet goes up in flames. You know, we have 4/5 of our atmosphere is nitrogen, and that kind of neutralizes that effect. You need the right planetary neighbors. You need large Jupiter-class planets in low eccentricity orbits. So what is that all about? Basically, Jupiter has a tremendously positive effect for us. Jupiter is a tremendously massive planet. It has a strong gravitational field. So when and it's sitting in an orbit that's almost circular. That's what low eccentricity is saying. So it's a circular orbit. It never makes an incursion into our orbit. If Jupiter were to have an elliptical orbit, in other words, a high eccentricity orbit, it would occasionally just come, rolling by and probably just grabbing us and making us a moon. If not, just shooting us off the solar system like a billiard ball. So we like Jupiter where it is, out there 5 astronomical units away in a circular orbit. And what it does is it draws comets and asteroids to itself like a big cosmic vacuum cleaner. It is cleaning up the solar system constantly for us so that we don't get hit with the comets and asteroids. So, in the early 90s, there was a comet Shoemaker-Levy that, was like on the news all the time, and people were, excited to go out with their telescopes and see it. Where did that thing go? It went into Jupiter. About some months later, there it was. Everybody was watching, there it went into Jupiter. So we are very thankful for Jupiter. All right, so now we're going to watch a movie for 5 minutes. Let's see if I need to click.
What safeguards our solar system is our star. The sun provides a shield stretching beyond the last planet in its orbit, a force field that deflects these cosmic rays. But these solar winds can be dangerous too, especially during outbursts called coronal mass ejections. Want a vision of Earth gone wrong? Just look at what solar storms do to our sister planet, Venus. They strip away lighter elements in its upper atmosphere, hydrogen, oxygen, and the molecule they form, water. What's left is a witch's brew of noxious chemicals, including thick, sulfurous clouds. How has Earth avoided the grim fate of Venus? We can see the answer as the solar storm approaches Earth. Our planet has a protective shield all its own, a powerful magnetic field generated deep within its core. In fact, that's just our first line of defense. Much of the solar energy that gets through is reflected back to space by clouds, ice, and snow. The energy that Earth absorbs is just enough to power a remarkable planetary engine, the climate. It's set in motion by the unevenness of solar heating, due in part to the cycles of day and night, and the seasons that cause warm, tropical winds to blow toward the poles, and cold polar air toward the equator. Wind currents drive surface ocean currents. This computer simulation shows the Gulf Stream winding its way along the coast of North America. This great ocean river carries enough heat energy to power the industrial world 100 times over. It breaks down in massive whirlpools that spread warm tropical waters over northern seas. Below the surface, they mix with cold, deep currents that swirl.
Well, it's really beautiful. It's called the Dynamic Earth, and it was made by NASA. It's just this amazing testament to God's creation right there in this video. So I'm going to stop it since we got to keep going. So far what we've been talking about has been sort of what I would call like theory, the astrobiology theory. Now we're going to go to experiment. What have we been observing? So what have actually been observations? So since 25 years ago, people have been able to now see planets around other stars. The reason this is difficult, and the reason it took only until the last quarter century, is that the star is about 1 billion times, or 10 billion times, depending on what size planet you're talking about in the star, brighter than the planet. So if the star looks like just a point in the sky, the planet is almost unseeable. The other thing is the planet is actually so close to the star that the star's light, basically, there's an optical effect called diffraction. It just kind of blobs all over the planet light as we see it. So that we don't really see the star at the size that it is. We see it at the size of how much it turned into a blob when it went into our optical instruments or our eye. Therefore, the way you want to see it is, at least the way they started trying to see it, is by looking indirectly at the star itself. So there are multiple ways to look at the star. And the reason is that when the planet goes around the star wobbles because in reaction against the planet's motion. That recoil is what you're looking for. So there are different methods. The original method was this thing called radial velocity. It was because if the star is wobbling, you can see it redshift and blue shift, a Doppler shift away from you. And this Doppler shift is like when you're standing in the side of the road and a car comes by you and it goes, meow. So that the high pitch turns into low pitch. It's blue shifted towards you and red shifted away from you. And that sound is a replica of this phenomenon. So if you do spectroscopy of the star and you see what the spectrum does, you can infer the existence of the planet. And that was what happened in 95 when they discovered the first. Another method, it relies on just getting lucky and looking at a solar system, stellar system, where the planet goes in front of the star and the star gets dim by a part in 10,000. Just tiny bit. If you're able to measure that carefully, you could detect the planet. But you have to get lucky. This stellar system could have an inclination at a different angle. The planets never look like they're coming in front of the star because they're in a different orbital plane. So it's not very good. There's another technique uses Einstein's relativity theory, and it's very complicated. Another method is you just take a picture and see if there's any planets, which sounds obvious, but it's that effect that I was talking about. It's only now in the last few years that we can do this, and that's actually the work that I do is in this area. But so here's this radial velocity, that first technique. The planet's going around the star, and you're looking at the spectrum from the star, and you're just looking at the spectral lines. You see whether they're shifting or not. If they're shifting, depending on what is the frequency, the amplitude, the shape, all of that tells you things about where the planet is and how heavy the planet is and all those things. The other technique is called the transit method. I was mentioning the Kepler mission did that. You can see here the dip in the starlight as the planet goes near it. And so that's using the transit technique, hundreds of planets have been detected, actually thousands now. And one of the lessons of this was that only a few % of sun-like stars have Earth-sized planets in their habitable zone. All right, so here's another lesson that was learned from the radial velocity technique. This picture is a little complicated, but it's for the population of planets that were discovered. You can plot on the horizontal axis the period of the planet, which is the same kind of analogous to how far it is from the star. So the star is this way, and the planet, this is where all the planets are. And this is how elliptical is the orbit. So up here at 1, the planet is essentially going like a line, just like this. Crazy elliptical. At the bottom is circular. And remember, we said circular is good. Jupiter is down here, would be about where that dot is. And notice that very small, I mean, most of this population is either too close or too non-circular. So very, very few of the planets are like Jupiter, of these Jupiter-sized class planets that were detected. This group here is called hot Jupiters, and they are very unfriendly. This paper basically says that what their modeling showed was that by the time a Jupiter-like planet becomes a hot Jupiter, it actually has come down into the inner part of the solar system, and in so doing has ejected all other planets. And that's why whenever you see hot Jupiters, you don't see anything else. It just destroyed them all. So you don't want hot Jupiters. This is data from Kepler, and this plot is a little bit hard to see, but this is a graphical way of showing at what radius from the star were the planets observed. And this azimuthal or positioning of these dots doesn't really matter, but the radial does. This is a log scale. And basically, this circle is 10 solar radii. That's like right next to the sun. And you can see there are planets that are even closer in than that. So when we have looked at other stellar systems, we see that almost all the other stellar systems have almost all of their planets inside of the orbit of Venus or Mercury even. Most of them are inside of Mercury's orbit. So they're just absolutely horrible. And in this paper they say, when viewed in this context, the solar system is unusual. And in another part they say, the raw contrast to our solar system is striking. So the big narrative is this. People would say, oh, we've seen billions of, there are billions of planets possible because we've seen thousands of them already, and therefore we're nothing special. But then you say, but that we are, because actually when you look at the data, nothing looks like the Earth. Nothing looks like the sun. Everything looks inhospitable. You know, it would not have been necessary for it to have been that way. It could have been the typical dynamics is such that all the orbits become circular quickly. It doesn't happen, it turns out. It happens, but it happens in a mechanism that actually destroys the other planets. So then you can take all this information, and you want to now systematize it to make a statement about what is possible, what's not. This man, Frank Drake, is known for something called the Drake equation, in which this came about when the project called the Search for Extraterrestrial Intelligence basically was trying to estimate whether they should go build antennas to look for radio signals from other intelligent beings. And they said, well, how many intelligent planets with intelligent beings where they could send radio signals should we expect? And they said, well, let's do it this way. How many stars are there? And they said, oh, maybe 100 billion with a B. And they said, okay, well, what fraction of those do we think would have planets? Oh, this much. Oh, of those, what fraction would the planets be the right kind? Oh, maybe this much. And of those, what fraction would actually life would spontaneously develop? And they had a fraction for that. A fraction that next week we'll argue should have been 0. Okay. But then they come up with, oh yeah, probably 100 million habitable, planets in our galaxy. And then of them, maybe 6 million would send radio signals. So in the 60s, they expected a plethora of radio signals from SETI. Now, fast forward to today, nothing. There is not a single signal. And the reason is that we can take the Drake equation and actually write all the new factors in. The modified Drake equation doesn't have 5 or 6 terms. It has something like 15 or 20 terms. Hugh Ross, a Christian astronomer, actually has like 120 terms. I think somebody told me recently he has 300 terms. He's maybe a little too fastidious. But Even at 15 terms, each of these you assign a probability of 10%. If they all have to be true independently, you have to multiply these probabilities. So you have 10% probability that you would have a planet. Of those 10%, let's say, have planets in the habitable zone. Of those, let's say 10% have plate tectonics and a magnetosphere, an axial tilt that's, and the right Jupiter-like neighbors. You put these fractions in, and it's like at the cash register, the price is going up. These 10%, when they multiply, you get numbers like 10 to the minus 15. Now, you have 100 billion stars, but you have 10 to the minus 15 probability that you would see anything. You end up with a number like 1 in 10,000. So you have to look at 10,000 Milky Way galaxies before you would have expected to see one planet with the characteristics that we know today we need to have. We may need to have more. But so that the expectation that there would be all these planets is actually shown not to be the case. This thing is called rare earth. There's a book called Rare Earth. Essentially, that this is more and more an understanding that is coming that the earth is actually quite rare. David, would you mind turning on the light? I think as we get to the end, it's good to just have the light on. Thanks. So now, the rare earth, people can answer by saying, oh, well, there's all these other opportunities in the galaxy and in the universe. And so you have to look at 10,000 Milky Ways. So what? There is 100 billion Milky Ways out there. So there is some Earth somewhere. So what do we answer to that? And the answer to that is that, number one, let's remember where we started. The start was that the Earth is nothing special. Well, now it's so special, you have to look at the probabilistic resources of the entire universe to think that maybe there would be somewhere else where you could get a habitable planet. And by the way, we haven't talked about life. That will be next week. This is just saying a planet that you could actually, with your spaceship land in and not immediately die. That's all we're talking about so far, right? So, but there's something more profound, and the credit for that discovery goes to Guillermo Gonzalez, who would have been here today. And it was the discovery that was written in a book called The Privileged Planet, which was that Guillermo observed that you have these requirements for habitable planets, but then you can ask a different question. Look at how amazing it is that we can discover so much about the universe. I mean, we can find out if another star has a planet, but we can't see the planet. But we can basically look at the Doppler shift from the planet, from the star, and from that infer this. Why is it that the universe lends itself to science? I mean, if it was just for Darwinian existence, all I need to do, like I said last week, is to be able to club my competitors and have as much offspring as I can have. That's all that Darwinism needs. But why should I understand the universe? Why should I be able to observe the universe? That is not, on a materialist picture, what I'm supposed to expect. And why is it that so much of the phenomena that's going on the Earth are amenable to understanding what the history of the Earth was? And they go through a whole bunch of lists of these requirements for habitability and how they correspond also to requirements for discovery. That correspondence is a different thing than probability. Why is it that, if you need an oxygen-nitrogen atmosphere to be able to breathe, that also happens to be the right atmosphere through which you can see the sky. If you had the atmosphere of Venus with CO2, that CO2 cloud wouldn't let you to see the stars. If you're near the center of the galaxy, remember that was supposed to be such a hot place? Well, it is a hot place, actually. It would be all blinding light all the time. The sky would be all just bright, like, super bright. There would be no visibility of the outer universe, which we do have out here in the suburbs where we live. Okay, so all of this. Now, here's an example that's very interesting. It has to do with perfect eclipses. So Guillermo observed that when you look at the eclipses are really fun, and those eclipse chasers, once you get hooked, you want to go wherever the eclipse is. But think about what an eclipse is. The moon gets in front of the sun, and the sky goes dark. But our eclipses are something really special that maybe is not always appreciated. The moon on the sky did you know, has the same size as the sun on the sky. The moon is 400 times smaller than the sun in diameter, but it also is exactly 400 times closer. So that on the sky, they both subtend 28 arc minutes, almost half a degree. They're exactly the same size, which makes possible that the moon can go in front of the sun and make what is called a perfect eclipse. You can have an oversized eclipse. If the moon was really close, it would just go wonk, there's no sun for a little bit, and that'd be interesting. But it's actually matched to the sun. And so that is interesting. Now, the fact that the moon is that big and in that size helps the axial tilt of the Earth to be stabilized. So we needed it for habitability. But the moon being the size of the sun in the sky makes perfect eclipses possible, and that makes a whole kinds of science possible that would have otherwise not been available. The first thing is, oh, by the way, here's an interesting plot. So this is also Guillermo's plot. Relative to, so you can think of all the possible places you can have eclipses in the solar system. There are 9 planets, okay, 8 if you want to argue. And then there's all these other, they all have moons. And so you can say, does that planet and that moon, could they make a good eclipse? And so you can say, what is the size of the moon relative to the sun on that planet with that moon? And you plot that, and you plot all these dots. And 1.0 is when the ratio is 1. In other words, moon and sun are the same size. And you can look down that line of 1.0, and there's our moon. And down here there's Prometheus. But that is around Saturn. Saturn is not a habitable planet, and Prometheus is a potato-shaped moon. Wouldn't make a good eclipse. It's just, So in fact, the only good condition is on where there are observers, which is very interesting. Now, what have we been able to do with these eclipses? Number one is that in the early 20th century, an eclipse enabled the discovery that the sun is a hot ball of gas, and it allowed us to do spectroscopy on the photosphere of the sun, which was impossible any other time. So that discovery essentially told us what the sun is made of, from which we then were able to understand what we should expect for all the stars in the universe. And so it leveraged our understanding of the entire universe. Another major discovery was Einstein's general relativity, where in 1919, basically during an eclipse, Eddington, who was Einstein's friend, showed that because of the gravitational shift of light, that the star ends up shifting relative to where it should be. So during the eclipse, it's a little bit hard to see, but if the sun wasn't there and the star is, let me see, which way does it go? If the sun isn't there, that star is there, relative to the background stars, you see it at that line. So everything goes outward. And so this picture, this is 2 images, negatives on top of each other, 6 months apart. One of them during the eclipse, the other not during the eclipse. And you can see the planet basically moves outward. And that proved Einstein's relativity, which then told us about the nature of gravity. And that was made possible by the eclipse. Now, there are a dozen other conditions. We talked about the atmosphere, plate tectonics. All of these things have to have a corresponding effect, corresponding efficacy for science. And that is just this amazing confluence of habitability and discovery. So in summary, what we find is far from being a sort of a common thing. The Earth is a really special planet with all these things rigged up, not only for us to live, but for us to look out upon the universe to see the glory of its creator. The fact that we can discover, the fact that we can reason, the fact that the universe is accessible to us should be surprising. And not only our minds were made, last week we were talking about how our minds were made so we can know that. Here we see that the machinery of the universe is made for us to discover it. It didn't have to be that way, but where the habitable planet is, there's also the opportunities for discovery. Psalm 19 says, the heavens declare the glory of God. So the heavens are able to speak. They're able to speak because we have this ability to discover. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge. They have no speech, no words, no sound is heard from them, yet their voice goes out into all the earth. Their words to the ends of the world. That the universe just is screaming about its creator. It was never meant for it to be neutral. It's just kind of amazing.